Timber Talks is brought to you by Wood Solutions. Stay up to date with the latest in timber, the building material that is strong, safe and sustainable. Here is your host, Adam Jones.
Hello everyone and welcome to the fourth part of this four-part series on the Best of Timber Talks, where we're pulling out the best stuff from over 50 episodes where we've spoken to world-leading experts and case studies. So today's topic will be all about design. And you'll hear from experts that are discussing things that range from timber-first design principles, fire engineering, durability, building physics, acoustics, design for vertical movement, and so forth. Firstly, you'll be hearing from Jennifer Cover, who's the CEO at Woodworks in the USA, on the 7 advantages that you can tap into when you design with timber. And secondly, we'll be hearing from Nick Milestone, the Chairman at Trada, on the importance of timber-first design. So we're coming toward the end now. You've got your finger on a lot of different projects and you deal with a lot of different consultants, and you know you've got a good understanding of where things are heading in the future. Do you have any advice for consultants listening in terms of how they can be the most relevant in the future for, say, what timber construction might end up being?
Yeah, I mean, I think that there is, kind of probably 7 key drivers to be thinking about when you consider mass timber. So the ones that we see as being of the most importance is the environmental side of this. It's an incredible environmental story. The aesthetic appeal is really important. The speed of construction, if that is critical to your owner, that is something that mass timber can really provide. Any urban infill type projects, so where potentially you want to add vertical density, you can, because of its lightweight, you're able to add it on top of other existing structures. Also, if you have tight construction constraints, that also is something that could be a driver. Labor shortages, again, if you have an owner who's got a project in an area where the cost of labor is really high, or there's a shortage of labor, it's something that could provide some stability with going with mass timber. Elevated structural performance is another driver. Again, the lightweight can really help with lower foundation costs. And biophilia, so kind of healthy buildings. So if you have an owner who's very interested in, perhaps capitalizing on some of these aspects that allow, lower stress in the work environment, just a healthier building in general. ULI recently did a study on the benefits of healthy buildings, and it's got some great information in terms of the reduction in sick days, productivity. It's really impressive. And, wood is just one part of that overall healthy building discussion, but it's a pretty important part. And so I think for architects and engineers wanting to set themselves apart, that it's a great opportunity to think about some of those drivers. And if you have a building owner who is looking at, kind of setting themselves apart, that you can really provide that to them by utilizing a wood solution, and Woodworks can help them if they're interested.
So we've mentioned a few times how we might be on the cusp of something new, and for the professionals listening, what do you think they should do if they want to become part of it? Because it sounds like it's moving to a more of a manufacturing and logistics exercise as opposed to at the moment where it's specialised. And if I'm probably saying the wrong thing, feel free to jump in, Nick.
No, I mean, crikey, we started on a journey of being presented with a building that was designed in concrete. And then what we're trying to do is rapidly convert it into mass timber. Each material has its different characteristics. It's got advantages and it's got disadvantages. We've got timber is a lot more short spanning. So therefore, if we ever get presented with a building in concrete and say, can you turn that into timber? Well, the simple answer is no. The best way to take advantage of the material is to design it from first principles. And I think when we did Dalston Lane, that was testament to that. So, okay, I'm quoting figures that were relevant about maybe 4 or 5 years ago, not relevant to current market conditions, but we were quoting GIFA rates of around 200, 225 a square metre. Because we designed it from first principles, we actually got the cost down to £185 per square metre for CLT. That will change now, more because of the market conditions. The CLT supply chain is in very much demand, so the economics of supply and demand is the price goes up.
And we had Brexit with the change in exchange rate, which made a huge change in the prices, to be honest.
Next, we'll be hearing from Emma Russell, who's a senior engineer at WSP, on what you need to look out for building extensions if you want to build on top with timber. Secondly, Andy Buchanan, director at PTL, and the use of post-tensioned timber systems. And thirdly, Hans Blaas, professor of timber engineering at Karlsruhe Institute of Timber Technologies. I struggle pronouncing that word. That's okay. On connection design fundamentals for timber. So looking forward, and we can move away from 55 South Bank, or you can draw from it. But if a developer's sitting on an asset now and they're thinking, what can we do with it? What are some of the things that they could look at to check if it is feasible to put, 2, 3, 4 floors, and it doesn't have to be 10 stories like 55 South Bank, but what are some of the things they could be looking at?
Yeah, so if there's, from a structural perspective, if there's existing capacity in the existing structure, or if it is necessary to strengthen, if that can be achieved without obviously compromising the existing architecture of the existing building. I guess the issue would be in terms of transferring, if you're doing a vertical extension, transferring the load-bearing elements, the load from those load-bearing elements onto the existing load-bearing elements. So from a CLT perspective, it had, with 55, it had, it's a hotel. So it has, you can have walls between every room. So that layout lends itself to CLT. Similarly with apartment buildings, whereas an office building would be different. So it does depend. It's going to be different for every building. Yeah. So it depends on the layout, but possibly if you are looking at an office building, you do want those open spaces. So it could be a combination of steel and timber, say. So there are definitely options, and that's going to be lighter still than using traditional concrete, even if the rest of the existing building is in concrete.
When I used to work under you and deal with concrete, I remember we'd design as an engineer to your 28-day concrete strength. But if you actually plot the progression of concrete over time, it actually strengthens. Do you think this is something that we might be able to tap into as well, and concrete actually is much stronger over time than during the construction phase of projects?
Yeah, so yes, the theory is that concrete does increase its compressive strength over time. So we would have expected, like 55 South Bank was built in the late 1980s. So it would have been expected that now a 40 MPa column would be higher than 40 MPa. The difficulty is in justifying that. Mm-hmm. So if you can take samples, you can do that and test that, but we found that it didn't always give the high results that you'd expect. Another option is for more recent buildings, every time you pour concrete, some of the concrete is used for testing purposes. So if you still got the results from those tests, it's usually a 7-day, 28-day. Sometimes it's a 56-day test as well. So potentially that would be the easiest way to justify if you had those concrete tests still available, and you could show that it did keep increasing and was higher than what it was designed for. But yeah, I think the difficulty is in justifying it. At least that's what we found, justifying a higher strength. But it's definitely, obviously, that's how you get your spare capacity. If the concrete strength of the existing structure is higher than what it was originally designed for.
Incredible. And one of the things you mentioned at the start of this podcast, and you've got a lot of experience in, is post-tensioned timber systems, which I understand you used a lot of for seismic purposes in New Zealand, rebuilding a lot of Christchurch after the earthquakes. Is there some utility as well for cores and stiffening up buildings as well?
Yeah, absolutely. And it goes like this. If you build structural walls in a multi-story building. They could be straight, flat walls on the edge of the building, or they could be tubular walls around your lift shaft and stairwell. But you've got to tie them down to the foundation. And the taller the building gets, the bigger the overturning moment gets, and so the bigger the tensile force at the bottom of the walls. And also the tensile forces between panels as you go up. And if you're not careful, you'll end up with huge steel plates with hundreds of nails at every level, and it becomes a mess. So one way of overcoming that is just to have a full height vertical rod. They might be quite chunky rods. They might be 30 or 40 millimetre diameter, high strength steel rods, which come from the concrete pre-stressing industry. They're pre-stressing bars, and they'll be anchored in the foundation. They run right to the top of the building. They're anchored off at the top, and they provide the tensile capacity, so you no longer have to have a connection at every floor level.
Mm.
Well, timber engineering certainly has changed a lot during the last, let's say, 2 or 3 decades. What we see today is really a move upwards, which has been made possible by 3 main reasons. One reason is the possibility of machining timber with computer-controlled machinery. The second reason is to have the mass timber products available, LVL, CLT, glulam. And the third reason is connection technology, which has evolved also to a high extent.
Mm. And at first principles, what are the connections trying to achieve? Because this is the area where I think you've focused most of your career on researching in this area.
Yes, that's right. What a connection wants to achieve is to, let's say, balance member capacities. So if the member capacity can be matched by the connection, then you can design economic timber structures. If connection capacities are below member capacities, then the members are over-designed. So good connections and strong connections are important to get member sizes down in timber structures. And we worked on that and have reached nearly 100% efficiency, we call that efficiency, in timber connections, for example, using self-tapping screws in softwood timber members. Now we have the challenge of using more hardwoods, and we have to repeat the exercise basically. If the connection can only carry 50% of the member capacity, then you need 50% of the member size really just to accommodate the connection. You wouldn't need that if the connection would be stronger.
In the next section, we'll be hearing from Rob Dixon, the Senior Fire Engineer at ARUP, on things to consider if you want to expose the timber in your building. Secondly, we'll be hearing from Karim Khalifa, Director at Sidewalk Labs, who's owned by Alphabet, another company who owns Google, on innovative fire solutions.
Well, I suppose the first thing we need to look at is all the characteristics of the building. So size, number of stories, floor plate, is it open plan, is it going to be cellular, is it residential, anything, all the characteristics of the building that we're designing for. And the second thing, probably from an architectural perspective, is to understand, what their architectural sort of aims are. So, if they're specifically wanting to expose timber because obviously it looks beautiful and, it shows off the sustainable credentials of buildings and things like that. And there's, lots of well-being positive issues about timber buildings. Obviously you're going to want to look at some of the timber. So then we need to understand, how much of the timber do you want to look at? Because for a bigger building, a higher risk building, which I think we'll probably get into later on, there's the design needs to be more and more stringent, basically, the higher risk the building is. And then, we can sort of start discussing things like how much of the timber they want to look at. We could try and sort of come up with a number, a safe proportion that they can expose, and also whereabouts in the building they can do it. We can come up with some sensible details to kind of break up the continuous combustible surfaces and things like that, and just work through things like that to try and sort of reach the architectural intent, but also to make sure we're designing within the sort of safe parameters. Yeah. So sprinklers operate generally between about 93 and 99%, so they're very reliable. So, but for the highest consequence fires, we must consider the 5% or the 1% where they don't work. So this is everything we do after that for a structural design is a redundancy design, but it's just to address the highest consequence cases.
Timber can be incredibly durable, and it just depends on the selection of the species and also the maintenance regime. Now, in one of the parks that I manage, we have park benches which have been placed now for 27 years, which have never been replaced. And because it's a quality hardwood that was purchased originally and with a good maintenance regime. So it has a light sand and a refinish once a year, and there's about 82 of these benches. And these seats look as good as the day that they were put in as a result of a good maintenance regime. And I challenge anyone who's got a concrete or a steel bench that would actually have seats that look as good, after 27 years being intensively used by the public. And what it does is that those seats are beautiful to sit on because they're timber versus, the hard, the coolness and the sharpness of, inorganic materials versus someone who sits, very comfortably on a timber park bench. So it gets back to choosing the right species and then undertaking a good maintenance regime. And we look after our timber assets in the park, and I look after my timber assets at home, and they're very old. With good care, timber can last hundreds and hundreds of years. And to me, the low energy consumption and the sustainability of the product is a product that we should go to first before considering other options in design.
One of the things you were talking about, again, in your keynote was about fire, which you take pretty seriously, because when we're talking about mass timber buildings, this is a challenge everywhere in the world. What is your approach to fire, and how can you help use some of the technology that you might be able to have access to and develop yourself to improve the fire design of buildings to be able to expose enough timber?
Yeah, so when everyone is worried about the fire and fuel contribution of mass timber. In reality, all the tests that we see across the world are showing that that's not really true. Nonetheless, we need to do our work to make it and minimize it as much as possible. So there's a few ways to do it. Obviously, the inherent value of mass timber is that you can encapsulate it with another layer of mass timber, and just like a smooth log put on the fire, it doesn't burn very well. It actually just chars and gets black. And as long as we don't get that heat to go into the core of that member, it doesn't ruin the structural integrity of the piece. And then you can chip off that blackened charred layer because it was sacrificial, and just add a new layer again, and the building will continue to perform. So that's the natural way of doing it, using timber itself. But we started to think is how could we actually cover the timber when we need to with another substance that was also green. And so drywall is the typical method, but we looked for something that was cradle to cradle, like I described before. So we actually found this ancient substance, I don't know if ancient's the right word, but 1,000-year-old substance from Japan that's called shikui. And we found that it actually had properties that probably could do this job very well of being a fire barrier. So we actually called some of the companies that manufacture this type of substance, the shikui, in Japan, and partnered with one of them to start testing and altering the application of it so it could protect our timber buildings. It turned out it's working very well for us. We did our testing already in laboratories. And then the other beautiful feature of this substance is it's antifungal. So we don't end up having mold issues either, which it is susceptible to some of the wall boards if they get damp. And so we can also take that substance now and spray it on the panels in our factory. And so all of our pieces now come fire protected to the site. So a lot of officials are quite worried about fire propagation while buildings are under construction and not really being supervised. And right now, all of our pieces come fire protected from the start. And so we really kind of started changing the formula of how people were looking at timber buildings being erected.
Yeah. That product sounds absolutely amazing.
And by the way, if it chips off or you have to get rid of it, you can just mix it in your garden.
Oh, really?
Yeah.
Oh, that's the best part as well. You also spoke about looking at the origination of the fire and how you can optimize and reduce the risk in that approach as well.
Yeah, so we looked at every piece of the formula, and there's kind of 5 different areas that we can talk about. But obviously, the best way to not have a fire is to stop it at its source. So fires really, about a third of the fires in most cities occur from kitchens or electric fires. So we went after, the first step we looked at was kitchens, what's going on with kitchens, and we removed natural gas. Now, we had a second reason to remove natural gas, and that was going to be to get rid of the greenhouse gas emissions. That's on that path as well. But when we removed it, we went to electric cooking. But when we started to interview the fire officials, they said it's not good enough to do electric cooking. We want to get rid of the heat source off the stovetop itself, which would be like a heat coil. And they said that a lot of people who have actually clothing, loose-fitting clothing, this is one of the fire sources, that some of the oils get onto the clothing, they get to the hot surface because they're cooking and their arm goes across, and that's some of the propagation of fire. Or maybe they pick up a towel from the counter to grab a pan or something. So we said, okay, let's go to induction cooking. And they said, well, that would be a game changer. So we got rid of natural gas, but we also went to induction cooking, which has a cool surface. So that was one step to get rid of it. And they said, well, if you do that, we think you could get rid of about 17% of our fire origination. And so then the second step was now we have a lot of electricity running around in the building. And we said, how can we go after that? So we've been looking at a technology that has digital electricity. And so this has been heavily tested. It's in many projects, probably about a couple of hundred actually, but never in a universal scale like going through an entire building, always used for specialty installations. So what this digital electricity does is if it shorts, it has a signal just like a data cable, and it says there's something wrong at the other end of this cable, I'm turning myself off. It turns itself off faster, 30 times faster than any other electric circuit that we have in the marketplace today. And so in this way, we now stop the propagation of electrical fires by the circuit being automatically turning itself off whenever it senses something like that. Our aspiration right now is actually to go all the way to the appliance and understand when you are toasting a piece of bread, how much energy that toaster normally uses. So with our digital electricity, we all can measure exactly the amount of energy that toaster needs at any one moment. So if one day it starts to demand more energy, we can turn that toaster off saying there's something wrong with this toaster. So the device, even if it fails, not just our wiring, can now be identified. So maybe, you went and you're reading a book and you put some toast in the toaster, you're going to get an alarm or maybe a message to your phone that's saying, we think there's something wrong with your toaster, we turned it off. And so wouldn't that be a great way before you burn the toast too bad?
Next in this podcast, you'll be hearing from Greg Nolan, Director of the Centre for Sustainable Architecture with Wood at UTAS, on the durability of wood, looking at really the first principles. Then you'll hear from Shaun Walsh, the President at AILA, Australian Institute of Landscape Architects, on the external use of timber.
The other thing about working with a natural material is that lots of other organisms have evolved to use that material through decay and to eat it. So with wood, if wood is left outside, it is then vulnerable to a whole range of biological forms of biological breakdown. And that's also then something that you've got to recognise in any building design. So if we unpack that a little bit, there are a couple of key methods of biological breakdown. There's two quite critical ones, and then there's a couple that are important to us for aesthetic purposes or appearance purposes. So it might make it unfashionable or unserviceable for us, but it's not actually going to lead to us having to replace it. So if we go to the two that then are quite critical, the first one is insects. So there are a whole range of insects that have evolved to enjoy eating the wood that we want to use in our structures. The most critical one of those, of course, is termites. And in most of Australia, termites are quite an issue. So there's lots of different processes, lots of different ways then of managing termite risk, which I think are far too extensive to go into here. But we've got to make sure that we manage exposure to termites. That's probably number one. The second one is decay. Decay occurs with wood that is wet and stays wet for a reasonable period of time. So decay is caused by fungi, and the fungi will break down the wood because it's their food. There's fungi spores in the air all around us. So if the wood is moist enough, so it's wet enough for the fungi to grow on it, then it will grow on it and it will start to multiply. If the wood is dry or was wet and has dried out, the fungi can't grow anymore. So there are certain bench lines, barrier lines for when the material is too dry for fungi. But effectively, if you can keep wood outside and dry, it won't decay. So even relatively low durability material, if kept dry outside, or is allowed to dry out very quickly after it gets wet, it will still last for a very long time.
Can you speak a little bit more about the potential risks of when moisture and water and the water content drives up in those building products, say where there might be timber or plasterboard?
Yeah, okay. So if we relate this back to the building code and the new clauses around the condensation management in the health and amenity section, it says that you shouldn't create ill health or perverse outcomes for the occupants. And when you start talking about health, you're saying, well, the first thing you need to stop is mold growth. And generally, if you stop mold growth, that's the first thing that occurs. But then you definitely, if you're going to prevent that mold growth, you're not going to get timber rot or anything worse happening. But if you do get mold growth and the moisture content of those materials starts to go up and up, and those materials are soggy for a long period, you can end up with worse problems. And when we start talking about timber as a general engineering rule of thumb, solid timber products, 20% moisture content by mass is a general threshold that you're designed to. And if you can stay below that, you're confident that the timber is going to be okay from a long-term durability perspective. When you start talking about engineered products, so the board products and plywoods and things like that, we generally use a rule of thumb of 18% moisture content. And these are conservative. 18%, 20% are conservative numbers. But in theory, they can probably hold much more moisture. But when you're engineering, you generally have safety margins built in. Like if you're building a bridge, you don't design it just to meet the thresholds. So that is what you want to do. And there are tools out there that can help you design construction systems and analyze the moisture within those construction systems to see if any of those materials are elevating above those thresholds.
In this final section of the podcast, we'll look at miscellaneous topics. So first of all, you'll be hearing from Jesse Clarke, who's the Building Science Manager at Pro Clima, on designing for building physics. Secondly, you'll hear from Amanda Robertson, who's the CEO at Marshall Day Acoustics, on acoustic design fundamentals. And then thirdly and finally in this podcast, you'll hear from Ryan Miller, a Senior Associate at Buehler, about designing for vertical movement. So looking at design now, if you were to design it, what kind of things would you be looking to detail with, and how might membranes assist with all of this?
Yeah, okay. So membranes are very important in the whole construction system. whether it be a wall or a roof, above grade, above ground systems generally. If we're talking below ground, you're talking about having the full vapor barrier stuff, but that's another story. So talking about above ground scenarios, we're talking about having sarking materials, and I say sarking because it's generally used in the industry, but we much prefer to use the word membrane. And membrane is, let's say, a lot more clever in nature, and the membrane that's designed to be that waterproof layer that sits behind the cladding, so it's the second line of defence, and that is going to make the system work from a drainage perspective when you're talking about drained and ventilated cavity systems. And that's what we promote as Pro Clima, those drained and ventilated cavity systems, because they've been proven internationally to work. If we start talking about face sealed system where the cladding is acting as the primary water barrier, essentially what happens is it cracks up over time. You've got thermal expansion, contraction, UV, all these weathering factors to deal with. Eventually it cracks and water gets in behind it. That's why you always should have this secondary barrier. And this secondary barrier is generally what's typically known as a sarking, but what we sell is vapor permeable membranes. And vapor permeable membranes are the ones we sell, highly waterproof. So they don't let water come through, but they let water vapor to escape out of the system to the ventilated cavity and expel that moisture. So if there was any moisture within the timber stud system, for example, it can dry out. And that's what we want. We want to make sure the systems maximise their water resistance or waterproofness and maximise their drying capacity.
So airborne sound transmission is the noise that comes from, say, one room into the next room. And it is a function of the constructions between the rooms. So if you've got a door between those two rooms, then typically the door is the weakest element in that construction. So that's when we're referring to sound insulation. It is the ability of the structure to reduce sound between the spaces. When we're talking about impact noise, that is the noise generated by things like footfall on a flooring surface that can be transmitted through the structure. So it's a different mechanism of sound. It's what is generated on the structure that comes through, if you like. For both of them, there's something which we call flanking sound, which is effectively the ability of sound to come through small gaps and construction detailing between the spaces. And that's an important aspect when we're talking timber buildings, because there's a lot of continuous elements between the spaces that need to be factored into the design that can carry that sound between two rooms.
And another really important aspect of design is the vertical movement within the building. How much movement did you design for per level, and how did you incorporate, or what did you look at to, I guess, mitigate any risk of structural damage to the building because of any kind of movement?
Okay, yeah, the vertical movement. The shrinkage of the wood members certainly is a little bit more, since we've got an added level of wood in the system. I think the number that we came up with was about 1 3/4 inches at the maximum amount, and so I don't recall what it was on a floor by floor basis. But I'd say we did use a semi-balloon frame technique where the walls have their top plates right up to the underside of the sheathing, and as opposed to a normal platform construction, which would have another plate in there, which would have more room for shrinkage. But other than that, we specify moisture content less than 19% to try to reduce how much it's going to shrink. And then, it's at that point, it's letting the architects and the MEP designers know about what our estimated shrinkages are, so that they can accommodate that in their own systems, like flexible couplings and joints and wall finishes and that sort of thing.
do those flexible couplings and wall finishes, does that add much cost to the project? These other elements that I guess are pretty novel if they were used in Australia.
Yeah, I guess I didn't have a good handle on what the cost was for those types of items. If I were to guess, I'd say they probably didn't add too much cost. It would have been, similar in the ballpark of what you would expect for a normal 5/1 podium type of project.
So shrinkage is obviously one big element of vertical movement, but there's also your compressive element, compressive strain within the building. And listeners may know that when we put load path through perpendicular grain, then there's going to be a lot more movement than it's going through parallel grain. So is there any other design criteria you have as you got the building to minimize perpendicular grain? I mean, do you entertain the idea of balloon framing or anything like that?
Okay. No, I think as far as I'm aware, I don't think we considered balloon framing here. That certainly would help to reduce some of that cross-grain compression, but yeah, I guess at the beginning stages, I think we knew we just wanted to go in with the semi-balloon and have it be, as much of a platform frame as they could for simple construction.
I hope you enjoyed that episode and learnt a few things when it comes to design. And if you're looking to learn a lot more, the best place to go is the Wood Solutions website to check out the Wood Solutions technical design guides. Right now, there's over 50 of them that touches on all the topics that were covered in that episode, whether it be durability, which would be guide 5, designing for vertical movement, which would be guide 50, designing for acoustics would be guide 44, and so forth. And I'll put the link in the show notes.